viscoelastic nunna. That adhesives like pressure epoxies we have seen, rubbers, foam material, thermoplastics. These are some of the examples of viscoelastic. So, if you see, star is the complex modulus, which mainly depends upon the storage modulus and loss modulus. E star is nothing but it is a complex number which mainly depends upon the storage modulus and the loss modulus. Loss modulus means it is the measure of energy lost, means how much vibrational energy is required to loss. That is primarily depends upon the loss modulus. Higher the large modulus, higher is good for us because that much of vibration energy is lost in. And storage modulus, it is a measure of energy stored. It is a E prime, and it is a combination of complex number. And we know the answer modulus is the stressless strain, and this is the main important parameter while designing the damping materials. So loss factor is nothing but the energy is lost by energy. This loss modulus mainly loss factor. Okay, the loss factor is nothing but the E star, E double star by E single star. That is loss modulus by storage modulus. It is a measure of amount of damping of the elastomer. Higher the damping, higher is the advantage for us. Because if the damping is more, the vibrational energy we can convert into the heat energy. So loss factor should be higher is required. The higher the loss factor, higher is the damping. So it is the make loss factor equal to inverse of the transmissibility. So transmissibility is nothing but the vibrational energy. It is transmitted from one system to, that is from input to output. So our aim is we have to transmit the vibration energy as higher as possible. It is a elastomer is sensitive to the loading and ambient conditions being imposed on the system. Okay. Tan delta is nothing but the loss modulus. Energy lost by energy stored. That we have seen in the complex number, real part by imaginary part of that complex. E star is equal to E prime plus I into E double prime. So that is the factor for the loss factor. So what actual meant by damping treatment is, it is a treatment which is applied on the like any foundations or any on the surface of the hull of the ship or any other region. We can apply that material and we can measure the, first we have to measure the energy levels, the vibration energy level, and you apply the treatment and again you measure the vibration level so that the energy is lost. But here what is the crux is what material you have to select it, how to design that material, that is the main important criteria. So it is a material, damping treatment is a material or a combination of materials applied on the structure to the increase the vibration energy dissipation. So this energy is to be thrown away. That is the main aim. How to doing, what material you have to set, what properties you have to set, that is our main concern, how to design the material. So if a large relatively thin metal structure is excited by mechanical vibration, a airborne sound or damping treatment applied to the structure supports results signification. Okay. So it depends upon the thickness of material also. At what is the thickness? We have to decide, we have to think accordingly what kind of material we have to apply. Whether we have to go for constrained layer or free layer, mainly depends upon the thickness of material. If the material thickness is less, we can go for free layer damping because the excitation, the conversion of energy is mainly because of the thickness. If the thickness is higher means we can go for constrained layer damping treatment. That I will explain. So damping is nothing but the dissipation of energy by converting the mechanical energy into mechanical energy of vibration, which is into vice versa or other form of energy like heat. It is adding the additional layers. So let us assume I will show the figures. let us assume we have the any foundation or we have seen the machinery foundation. It has certain plate thickness, some stiffness will be there, bottom plate thickness will be there. So if you want to reduce the vibration energy on the structure, viscoelastic layer, the what kind of viscoelastic layer that we have to decide. We have to, that property we have found out, that has to be bonded on the structure, and above that one more layer, metallic layer, you have to bond. So bottom material thickness, let us assume 10 mm or 50, 100 mm thickness plate is there. Above that, you have to apply that vibroelastic material, rubber material. The property as rubber we have to finalize, and above that one plate, thin plate also to be bonded, such that the conversion of energy is transmitted as a, there are two types of CLD, FLD we discussed now. The one is through bending it will transfer, one is through shear deformation it will take place. So we have free layer damping treatment and constant layer damping treatment. Then tuned mass damper that we have. Mainly these are two are damping treatment. This is the stiffness mass reduction. So we will discuss one by one. So if you see free layer damping treatment, this is, let us say this is the base layer, that is our foundation layer. Above that viscoelastic material you can bond or we can paste on the structure. Then when it is vibrates, the energy is transmitting from base layer to damping layer by using shear deformation, by using the extensional deformation through bending. When it vibrates, it bends. Because of that, the vibration energy is transmitting to the top layer, and that energy is converted as a heat. But the quantity of heat is very, very minute. We measure the temperature, very 5 degree or 2 degree change is there. But the huge vibration energy is higher energy that we can dissipate. And this is the CLD, constant layer damping treatment. Let us say this is the vibration structure, and this is the viscoelastic material, rubber material. Because different types of rubbers will be there, we have to choose natural rubber. And the property we have to identify before doing the finalizing the material. You have to do analytically, we have to prove, and then that composition if it matches, if it do the analysis, if it is okay, then only you have to fabricate and apply. This is the viscoelastic layer. Above that one more layer is there, that is the base layer having 1/10 of the thickness. Let us assume this is 10 mm and that is 1 mm thickness is required. That will be when energy's reduction by using the bending of the waves. These are the two types of structures. So what we are doing, we are increasing the damping to the structure. Whether both the ways, whether it is CLD or FLD, both the cases we are increasing damping. If you increase the damping, what will happen? More rapid decay of unbalanced vibrations. So very fastly the vibration energy will convert or will reduce. And also faster decay of freely operating structure borne waves. So we have seen the vibration, the airborne, structure borne and underwater. The structure borne noise or structure borne vibration we can freely propagate and that will decay a lot fastly. And amplitude of the vibration at a resonance structure will be reduced. Our aim is amplitude should be as less as possible. At the resonance, so we have seen the transmittal curve. At the resonance omega is 1, there the amplitude is high. So because of the damping treatment, the amplitude at the resonance condition will reduce. So we have seen that curve. So mainly because of the damping only, amplitude at resonance condition reduces. That is, we have seen structure borne, mass, stiffness borne, and the amplitude level, there it will be reduced because of the damping. So this is the equation, governing equation where these three scientists, Ross, Kelvin, Unger, RKU equation, what we call. This is the eta by eta 2, loss factor by eta 2 is the loss factor of damping material. This is the system loss factor. Mainly, eta is if it is more, higher loss of the energy. So it mainly depends upon the E and H. E is nothing but the N's modulus, E1 and E2. N's modulus is the bottom material, N's modulus of viscoelastic material. H1, H2 is the thickness of the material, like the bottom layer thickness, viscoelastic layer thickness. So mainly depends upon the system loss factor, is mainly depends upon the N's modulus ratio and thickness ratio. So we have to design the material accordingly, and we have to find out the higher loss factor. If it is higher loss factor, then more vibration energy we can reduce. That is the equation. So if you see, this is the nomogram. We want to design, because this is the loss factor, this is the thickness ratio, and this is the N's modulation ratio. So our aim is loss factor should be as high as possible. So ladies and gentlemen, I want this graph, this line. Basically it is not possible because it is very, very high. Ladies and gentlemen, I want the 0.1, eta by eta is 0.1. Then in that case, you can select either this graph or this graph, this graph, this graph. If you select this graph, what will happen? This is the point, and eta 2 by eta 1 is 0.1. So we have to design the material of the bottom layer and viscoelastic material layer such that the N's modulus ratio is equivalent to 0.1. If you design, we have the steel material is there, that N's modulus we know. Viscoelastic material, that combination we have to do such that N's modulus ratio is 0.1. If it is steel N's modulus, let us assume 10 meter, let us assume, and that eta E2 is, if it will become 0.1 means let us assume 1. It should be, if it is 1 N's modulus, steel metal 10, then 1 by 10 is 0.1. Like that, we have to design the viscoelastic material N's modulus, and if you design the material such that if it is equal to 0.1, then after that, the thickness, you have a thickness ratio you have to find out. Let us assume this is the material, then H2 by H1 is let us say 1 means this is 0.2 or 0.3. So then like that, the thickness of the material you have to select. Bottom layer thickness, viscoelastic layer thickness, that thickness will get either 0.1, 0.2, 0.3, 1, 2 depending upon the required isolation. Like this, you have to select the N's modulus, you have to find out the N's modulus, thicknesses depending on required isolation. Higher the isolation, better for us. So, but if it is feasible or not feasible, we don't know. So N's modulus, the combination of chemicals, some substrates are there. If you mix that one, whether we will get that N's modulus, that we don't know. So required N's modulus, how much you are getting, whether it is 0.1 getting, 0.03, 0.1, like that, you have to compromise. I don't have any material. I am not selecting material. I am not getting 0.1. Then if you get 0.03, then your loss factor is reduced. You won't get higher vibration loss. That is, the vibration loss reduced. Further, if you want to reduce, or further if you want to increase, you have to take the N's modulus as a criteria. In addition to N's modulus, like shear modulus and curves are there, you have to calculate, and something you have to compromise also. If it is not possible to do everything. Like that, we have to trial and error method you have to do, and then found out the N's modulus is thickness ratio, loss factor ratio. So, like free layer damping treatment, let us assume this is one of the structure. This is the one of the structure in the ship. This is the one of the structure in the outside structure. Basically, this is the material like MS or steel. We can measure the vibration level at this location. You have the vibration reduce more. And if you want to reduce this damping material like substrate, free layer damping material, this is the combination of viscoelastic material and some pigments are added. All this material you have to mix it. First we have to do the design. Once it is composition finalized, you have to mix thoroughly both all the material, and then you have to find out that viscoelastic material, and then you have to apply. Some it is required some curing time after 24 hours or 38 hours. Then you can measure the vibration again. Then the vibration energy will be reduced. Like this, you have to do number of experiments, number of locations where the vibrations are more. That is, we have carried out. It is a paste-like structure, viscoelastic material, having consisting of polymers as well as binders and pigments with some of the additives. The composition here, main crux is the composition. Then only we can decide that we can find out the vibration. So this will be applied, measure the vibration level before and after, and reduction of the levels are observed. Like this is the one of the small barge. Before going to ships experiments, we have to go for inside the laboratory, some barge is there. This is the compressor which creates the vibrational energy, and we have to measure the vibration levels before and after the application. There is a drastic reduction of the vibration energy, around if you see 10 dB, 20 dB of vibration level was reduced for a broadband spectrum, like frequency to 10,000 Hz. In that, if you see the broadband, there is a drastic reduction in the vibration energy observed. This is the before vibration level, higher the level, after application FLD, this is the vibration. And this is the CLD, constrained layer damping treatment. This also mainly depends upon the, it has 3 layers. We previously FLD having only 2 base layer structure and the viscoelastic, not viscoelastic, that is the extension damping. And this is the RKU equation which consisting of 3 layers, both base layer, viscous rubber layer, as well as the again metallic substrate. These 3 layers will be there. And this will be mainly the conversion is because of shear deformation. Shear is because of one layer to another layer, because of the shear stress, this will be energy transfer takes place. This is the RKA equation mainly. It is also mainly depends upon the Hence moduluses. This is the last factor. Hence modulus, thicknesses, as well as the shear modulus also. Here we have the, yes, G is there. Yeah, here G is there. So G is the shear modulus of the material, Hence modulus of material, thickness ratios. Mainly here the last factor mainly depends upon the 3 parameters. There only Hence modulus and thickness. So all the 3 layers, H1, H2, H3 here. H1 is the bottom layer thickness, H2 is the viscoelastic layer, H3 is the substrate thickness. And shear modulus of total structure mainly depends upon the Hence modulus, density, as well as the thickness. And D is nothing but it also depends upon depending parameter, and which depends upon the Hence modulus, thicknesses, and the shear modulus. So we have to design the for a particular loss factor. All this plays a vital role. It is a complex number where mainly depends upon all the parameters. So this is the CLD mainly applied on the frames, metallic frames, or engine room, one of the compound where the engines will be resting on the engine room. This is the compressor base frame. This is the base frame of one of the machine, and this is one of the bar structure. So experimentally we have done in the laboratory first, applied that viscoelastic material as well as the substrate on this, like this we have applied, and this is the top layer, this is sides, we applied the material, and again we have found out the vibration energies before and after, and there is a reduction of the vibration energy around 20 dB observed for a broadcast structure. Like this, so many number of experiments we can go for, like not only engine room where the complete structure also we can go depending upon the requirement where we want to apply. Like that we have to measure the vibration energy. And third one is the tune mass damper, where this damping is nothing but that it mainly depends upon the mass and the stiffness. It mainly reduces the amplitude of tonal frequency reduction. You see the spectrum graph, at natural frequency amplitude is high. That tone amplitude, if you want to reduce, we have to apply the tune mass damper. Amplitude at the resonance frequency we can reduce by using tune mass damper. This is spectrum where the higher amplitude is there. This amplitude it will convert to lowest amplitude. So we have to This is a tune mass damper. It depends upon the stiffness as well as the mass of the system. You have to design the stiffness such that omega and root k by m, such that natural frequency of this material equal to natural frequency of the base material. Means that is assuming it is vibrating at certain energy, it has certain natural frequency. If you create some equipment such that both the natural frequency matches, then you have to assemble at 4 locations. Then instead of vibration of the machine, it will transmit to these 4 tune mass damper. This will vibrate, but this will be in safer condition. That is the main aim of tune mass damper. So our main equipment will be survive. These small TMDs will vibrate, but that won't create any harm to the machinery. That is the tune mass damper. Here main crux is we have to increment the natural frequencies. That is the main aim. So same this TMDs we have developed. So all these peaks we have reduced drastically. Like the TMDs we can assemble all three directions X, Y, Z and all the 4 places. Like one is this is the vertical direction, horizontal direction, lateral direction. Like all the 4 places we can apply. Like 1, 2, 3, 4. Small one. Finally, these vibration levels we can reduce. That is the main. It consisting of mass, length of the rod, diameter, type of mount, what type of mount we are using, what is the RPM of the equipment. All this plays a vital role while designing the TMDs. So, because of the speed, we will get the RPM, natural frequency, and because of the length and the diameter and mass of this equipment, we can find out the same natural frequency. We can apply and we can find out the energy levels. So, amplitude we can reduce it. And next one is MR damper, magnetoreological damper. Here, main crux is the density of the material will change if we apply certain voltage. Normally, initially it will be fluid condition. The damping material we can apply. Initially it is fluid. If you apply that voltage, it will create some damping between it will create some columns in between the layers, so that the energy viscosity of the fluid is increases. That is how it will do. Like it consisting of some fluid where it consisting of iron particles and suspended molecules. So mainly is rheology. Rheology of the fluid will be changes by application of the magnetic field or the electric field. That is the main aim of. It is a electro-rheological fluid, and voltage across the electrodes, if you change, then the viscosity of the fluid will reduce. That is the main aim. Mainly the fluid mainly consisting of iron particles, of suspended liquid mineral oils, synthetic oil, water, vapor. This will be combination of that. We have to decide this material composition. We have to decide before that. Then it will be voltage applied. So, like if you supply the energy, it forms a magnetic field, and then it creates some layers or some closed environment. Then it will be solidified. That is the main aim of the MR damper. It creates the chain-like structure. It restricts the fluid motion. That is the main aim, and then viscosity increases. So different types of MR dampers that we can apply below the engine or at the 4 corners of the controller. So different applications we can do that. Then finally, this is all these dampers what we have seen, the passive damping techniques. Whatever we have seen, vibration isolation, vibration damping, TMD, tune mass damper, MR dampers. These are passive vibration technique. So what passive means? We are controlling externally, but we are not controlling the input vibration excitation. So if you do the active, means the input excitation you can convert such that vibration levels are minimized. That is by using the active vibration control. So to reduce the vibration of mechanical system by modification of system structural response. Let us assume the structure is vibrating. We can measure that vibration level, and by using the sensor we can measure, and then by using actuator system, if you create the excitation in opposite direction, Like assume the structure is creating like this. If you create the vibration opposite direction, such that it will nullify, it becomes a zero. That is by active vibration control. So mainly it consists in a sensor. Sensor is used to measure the vibration, the accelerometer, to measure the vibration level. That level fed to the controller of the system. The controller, it manipulates the signal. So the input signal converted into output signal, completely opposite, 90 degree, 180 degree opposite, and that it will create the vibration by using the actuator. It will create the mechanical response. That is the main aim of the sensor, controller, and actuator. Some examples are like actuators are there, semi-active and fully active actuators are there. Means the mechanical, it supplies the mechanical energy. So, like again we have to create some energy opposite direction. That purpose will be doing by using actuator. Like we have vibration shakers are there, electrodynamic shakers are there, or piezoelectric ceramic materials and electrohydraulic devices. By using these equipment, we can do artificially excitation. And semi-active is it stores or only dissipate the energy. Ours is a fully active. So this MR dampers, what we have discussed is the semi-active material, and the fully active material is the active vibration control by using the vibration shakers and the vibration. So if you see, let us assume this is our system where the input excitation is coming to this place. So then it will vibrate like this. Then let us assume if we don't have any this system, the output response is more. But I want to control this vibration. It will be in stable condition only. Then the vibration level will measure the sensor accelerometer. That value distributes to the controller from the signal conditioning element. The controller will again amplify the signal, and that it will send the signal to actuator. So finally actuator what it will do? That is the energy it is giving in this direction. This actuator will give opposite direction. Means both are in opposite direction, so that this will be in amplitude is minimized or reduced. That is the main aim of this active vibration control. There are different types of active vibrations are there. Another example same. Acoustic wave is coming in this direction, but this plate I want to be stationary condition. Then sensor will measure oppositely, actuator will give opposite direction. This is the primary source, this is the secondary. Finally, it will be in stable condition. So you got the primary wave in this form, and you are supplied the secondary wave opposite direction. Finally, my residual signal is 0. This is the active control phenomena. Again, there are two types: active feed forward control, feed backward control. Feed forward control is what we have discussed initially. The excitation, input excitation here is coming. The same input excitation you take, and again you supply the required signal in the opposite direction. That is feed forward. We are taking the response from the input signal. Again, if you take the response from the system, that is feed backward control. Mainly where you are taking the input signal, mainly depends upon whether it is feed forward, backward signal. So again the same sensors, feedbacks and control system will be there. So like this, this is the active vibration control for a typical response curve. Where let us assume this is the control. Without controller, the excitation is like this. With active vibration control, it will be minimized drastically around 20 to sometimes 20 dB, 10 dB reduction. Mainly this will be applied where it up to low frequency of around 500 Hz or 200 Hz, 300 Hz. Normally damping and isolation we can apply 10,000 Hz also, 10,000, 20,000 Hz. But active vibration control still area we have to do lots of R&D so that we have to enhance the frequency levels. Still work is less. Nobody I think very small, very less people have been done. R&D activities are taking there. This has to be improved a lot. This is the active vibration control. Till now we have seen the vibration reduction technique and some of the noise control devices, like noise is the sound, how to reduce the sound, some of the treatments are there. I just explained. If you see, yes, all these are acoustic silencer and enclosures acoustic. What it will do, like acoustic silencer, what it will do, like input, like we have the in the ships, some input air is to be sucked. But when it is sucking, at that velocity, huge noise is generated at the source level. What we have to do this, we have to create some any equipment such that the input sound level we have to reduce. Then that is the acoustic silencers. Or some machinery is there, like pump or any compressor is creating. You have to design the material such that if you keep the equipment on this acoustic hood on the equipment, it will reduce the sound level. Or acoustic enclosure. The complete equipments are there which is creating some noise. You have to design such that all these equipment enclosures we have to make such that the vibration or noise levels are minimized. That is the main aim of this noise control devices. Basically, it consisting of passive noise device. We are not the active device. This is a passive control device. Consisting of sound absorbing material, that like rock wool, glass wool, mineral wool, different techniques are there. You see this material also inside that panels are the acoustic panels. It consisting of rock wool material inside, where it will control it will absorb the noise energy. Like that same treatment we have to apply on the engine room of the ships. The selection of the material plays a vital role here. What it will do is dissipative silencers. It converts the acoustic energy into, there are, if you see the automobile engine, there are two types, passive vibration control and the dissipative silencers. In the dissipative silence, the performance silence mainly depends on geometry. In the dissipative silencer, what it will do, it converts the acoustic energy, it will passes through the path, and the acoustic energy again it will convert into heat energy. So in damping treatment also vibration energy converted into heat. Here also acoustic energy converted into heat. By what the friction it will create when it is passing to the duct, it will create some energy when it is passing, it creates some frictional force. Because of that heat is generated, because of the noise will be reduced. That is the main aim. It creates the friction in the voids between the oscillating gas particles and the fibrous pores, sound absorbing material. So again, crux is the how to design these parameters. What type of material? What is the properties of the material? Depends upon the input signal that we have to design. Like one of the onboard ship, this is the gas turbine intake silencer, where initially without the silencer, if you see this one, huge sound is created before that. And by designing the baffles, this is the what we call the baffles, where it consisting of rock wool material. Some of the holes will be there. You have to design the holes and material design also another technique. And create such that if you measure the noise level, use noise levels are reduced after implementing the GT intakes. This is what we call the silencer, and we have to measure the sound level before and after. Where it, after completion of experiment, there is drastic around 100 to around 20 dB noise reduction we observed spectrum of the broadband spectrum of 250 to 8. So we have to mainly consider material of the baffle material, and what is the hole diameter, what is the location of the holes, how much holes we have to keep. This we have to do. Similarly, the silencer we have kept for the ventilation fan. One of the ships, we have to create that ventilation fan silencer. Again, the same technique we have to implement, and noise levels are reduced. Same technique we have to implement, different applications. Here the sound absorbing material is a rock wool, and around 15 dB noise reduction has been observed. Similarly, a gas turbine exhaust silencer, where we have seen that where the exhaust energy which is coming from the ships, it creates huge noise at the nozzle. For that again we have to design the silencer, and again the rock wool material we have to like along the circumferentially we have to create some cylinder having the sound absorbed material, so that when the noise is created, this sound will absorbed by the silencer. And mainly the length, the diameter, thickness, the gap between this, and what is the material. Here we are using rock wool of different density. And finally we have found out the insertion loss. Insertion loss is nothing but what is the noise energy before inserting the silencer, and what is the noise level after implementing the silencer. We have to find out. That we call the insertion loss. Around 12 dB noise has been reduced. Like that, so many applications we have seen. Basically, this is the acoustic panel. What is there? There are 3 layers are there. If you see these panels, here is the impedance sheet is there. In between this outside is perforated sheet. In between this sound absorbing material will be there. Where when the incoming sound wave passes through this one, it creates some voids. Where when it is passing, the sound energy converted into heat energy, and this the energy is sound absorbing material, and this sound energy will be reduced. That is the main aim of this acoustic panel. Impedance sheet, it retains the sound energy. This is the impedance sheet, and second is the porous material. It absorbs the sound energy, and this perforated sheet is it is a mechanical structure where it will be operated. This is the concept of the acoustic panel. Like this, again, different types are there. The enclosures are freestanding large, freestanding close fitting. This is a close fitting. There are, depending upon the size, we have to design the enclosures. Again, that insertion loss, that is it mainly depends upon that sound power radiated by the enclosure by corresponding sound pressure there. It is a ratio of tunnel W1 to W. Finally, isolation loss should be as high as possible. We have to design the material such that the isolation loss should be highest. Like this is one of the enclosures designed for one of the ships. So different classes ships of different designed for different applications. So first, what development process? What we have to collect the data first. What is the sound energy emitting by the respective equipment, and we have to find out the acoustic material. What type of material we have to choose, depending on the properties. The rock wool, glass wool, iron wool. Depends on density, porous capacity, and then we have to determine the configuration. What shape, size we have to do. We have to fabricate the structure, and we have to evaluate. Again, we have to find out the sound energy level, and then we have to apply on the. We have to go inside the ship and apply, and again we have to measure the noise level. That is the complete work. So this is one of the ships. This is the alternator enclosure. It is very complicated place. Is very constrained. So again the same design we have carried out. Applied at the one of the ship of the diesel alternator. And this is the insertion loss around 15 dB noise level we have reduced drastically. These are the configuration of the material. And this is the acoustic tile, one of the typical submarine outer hull. The rubber material we have to select such that it will be bonded on the surface of the outer surface of the submarine. Main aim is it won't allow the incoming noise to the outside, because if it allows means in the inside what enemy will detect, and also what is the outer noise which is coming towards the submarine, it will absorb. So both outside the inside it won't allow, inside to outside also it won't allow. That is the main aim of this acoustic tile. It is a non-uniform rubber-like material having the different physical and mechanical properties that are bonded to be that certain the properties, different properties will be there. Finally, we want to arrest the movement of the sound from inside to outside, outside to inside. That is the main name of this acoustic tile. So the acoustic tile, before applying on the submarine, in the laboratory experiment we have to carry out, and we have to find out the insertion loss on the bar structure. This also decoupling tile also. Similarly, we have to find out the insertion loss or the reduction of the noise level. So till now we have completed the vibration as well as the noise control treatments. Now in the stealth, if you see in one of the first spectrum, first is the vibration reduction, noise reduction, IR. IR is one of the temperature which is identified by the enemy. That is also we can control. Then RCS, ELFE, MAG. Different techniques are there, but I will discuss IR and we can stop the lecture. IR is the infrared radiation. The enemies detect the temperature of our ships. If the temperature is higher, he will identify our place. So what the IR is, if you see the spectrum, there are frequencies, vibration, electromagnetic spectrum, like radios, micros, IR, X-ray, gamma rays are there. So it will, the wavelength frequency is increasing. Finally, our concentration is IR, mainly depends upon this region, from 500 nanometer to some 5. This area is the main area where the enemy will detect. That frequency as well as the wavelength is the main important area. Like the sources of temperature of the ships, that is, if you see the hot spot, exhaust, engine room, we have the temperatures are more, and exhaust is the exhaust gases where the high temperature will be there, and duct, the front engine duct is a high temperature will be there. These are the sources of temperature, and these are the inside that, and the external sources of radiation, sky and atmosphere. So the exhaust duct is the main contributor for the radiation. So we have to find out the path from the source to receiver, and we have to reduce the temperature of the path. Okay, and before that we have to do the analysis, and we have to find out the complete temperature and how to reduce the hot spot of the temperature. So if you see the hull temperature around 30 degree, plume temperature, plume is the exhaust gas center point in the plume around 380 degree, exhaust duct temperature is 380 degree. So all these temperatures, if you arrest, we can reduce the temperature. And this is one of the ship's temperature points. This is the comparison measure versus predicted. And exhaust, we have seen the exhaust, gas turbine exhaust, both temperature also high, sound also more. So that's why thermoacoustic silencer, the name is, it will reduce the temperature of the exhaust gases as well as the sound energy of the exhaust gases. It is a combination. By using single equipment, we can reduce the both noise as well as the temperature. Thermoacoustic silencer, where it will find out the first we have this transition noise. This is a mixing tube. These are the baffles. So if you this is the exhaust gas which is transmitting to the final well. So we have to design the silencer such that both temperature as well as the sound energy we have to reduce. So this is the ANSYS model. Before doing that, we have to find out the dimensions, and we have to carry out the temperature thermal analysis. That is, these are the when the flow is, gas is flowing at different velocities, what is the temperature coming on to the structure that we have found out. And 480 degrees, which is coming at the bottom layer, and outer layer 55 degrees. So this experimentally we have carried out one of the naval dockyard. So experimentally compared theoretically and experimentally we have found out. So with this, with the trials we have carried out, this is the without IR access device. The temperatures are this 270, 350 and 60 degrees. With the incorporation of IRS device, temperature drastically reduced from 270 to 50 to 68. So 81% reduction of the skin temperature you have observed, and plume temperature 23% reduction of the temperature. So like this we have to design that silencers, thermoacoustic silencer. These are the best results. So how to some water injection techniques also there. So when the gas is flowing from the mixing tube, you have to inject some water vapor from the bottom, so that both the temperature as well as sound will be reduced. These are the water injection system measures. And this is the CFD analysis of what is the temperature across the fluid water injection system. Before and after, how much temperature reduced. And the type of nozzles are depend upon the nozzle lobe type. Let us assume this is a lobe type where we can reduce higher temperature. One of the exhaust temperature nozzle design. If you use compare normal nozzle, cylindrical nozzle, if you use lobe nozzle, we can reduce the temperature more. That is the CFD analysis. This is the IRS device. So we can stop this. Again, is there any other question?
So, any questions you can